I just want something that can spin forever. Is that too much to ask? A fidget spinner in a vacuum chamber doesn't have air resistance, but it still has resistance from the bearings, so it eventually stops. A spinning top repelled by a ring magnet below eventually falls, even in a vacuum chamber with no air resistance, due to gyroscopic precession. Even a superconductor with a spinning magnet on top eventually stops in a vacuum because of tiny induced currents because it's a type 2 superconductor. But I think I've found the solution: axially symmetric diamagnetic levitation. This is a form of levitation that can happen at room temperature with essentially zero resistance without needing a superconductor. In this video, I'm going to test whether I've finally found a way to achieve never-ending rotation with no energy input. So I got this idea from researchers at Okinawa Institute of Science and Technology. They sent me an email saying they have a way to allow frictionless rotation using diamagnetism. Now, diamagnetism is a special kind of magnetism that happens anytime there are filled orbitals in an atom. And guess what? Every atom except isolated hydrogen has filled orbitals somewhere in it. So everything has some amount of diamagnetism. That's why you can push water around with a strong magnet. This basic diamagnetism is called Larmor diamagnetism, and it comes from the gyroscopic precession of electrons in filled orbitals, creating their own magnetic field when exposed to a stronger magnetic field. So all insulators like water, wood, or anything else you can think of repel a magnet slightly. But there's another much stronger diamagnetic effect that happens in conductors. For example, I have some pyrolytic graphite here. It's a bunch of carbon atoms bonded in such a way that they essentially have one large orbital containing free electrons. And these electrons can buzz around from atom to atom. It's basically like a gas of electrons called a Fermi gas. So when you apply a magnetic field to an electron that's already moving, the field makes it curve and move in a circle. This is called the Lorentz force. This electron that now moves in a circle produces a magnetic field that opposes the original field that made it move in a circle in the first place. So this whole gas of electrons is repelled by the magnet. This is called Landau diamagnetism, and it's orders of magnitude stronger than the Larmor diamagnetism we saw with water. It's so strong that if you just take a piece of this pyrolytic graphite and place it in a strong magnetic field gradient, it will levitate. The force is strongest where the magnetic field changes the most. So right at the edges of the magnet is where the gradient is the steepest. So you can see it floats right near the edge, but in the center it doesn't float. That's because in a uniform field like the center of my strong magnet here, there's still a strong diamagnetic moment, but to create a force you need a magnetic field gradient, like near the edges. So in order to make it actually float, we have to arrange magnets alternating north and south facing upward. This creates strong field gradients at the edges of the magnets. So if I put the square graphite on this magnetic pattern, it traps it in the middle and levitates it. But wait a minute, this whole thing was supposed to be about getting something to spin forever. Where's the spinning come into play here? Notice when I try to spin it, it slows down almost immediately. This is because of yet another Lorentz force effect. We're taking these bulk electrons in the graphite and moving them through a magnetic field. This causes the electrons to form little current loops called eddy currents. Eddy currents happen whenever you move a conductor through a magnetic field, and it slows that conductor down. Like when I try to drop this piece of aluminum past my magnet, it slows down near the high concentrated edges. So if we're going to spin something on these magnets, we need a magnetic field that's rotationally symmetric, meaning it doesn't change no matter how we rotate the conductor on top of it. And that's what this setup is. I have a ring magnet with a cylindrical magnet in the center so that the tops of the rings are north and the top of the cylinder is south. So we have the alternating north-south that we need, and it gives you a strong field gradient, but now it's the same in every direction rotationally. Now watch this. When I put the graphite on it, it can just spin freely. It's stably held in the center and it can rotate freely with no eddy current slowing it down. So that means the only resistance we have to deal with now is the air. I can use a circular piece of graphite and you can see that once it starts spinning, it just goes and goes. But will it spin forever? Well, let's see how long I can get it to rotate in the air, and then I'll put it in the vacuum chamber and remove the air to try to get the perpetual motion I've always dreamed of. But first, if you like watching my channel, then you probably love doing your own experiments as well. That's why I want to tell you about our sponsor, Mel Science. One of the best ways to learn about something is by doing it yourself. And their science kits bring that experience right into your home. Mel Science Kits are a subscription box delivered monthly. They have a lot of different options like chemistry kits, physics kits, and even kits designed just for kids. For example, if you like magnetic levitation, you can do your own using their magnetic levitation kit. Their boxes are my favorite science kits because they have so many unique projects and give you everything you need to do the experiment. They also make great gifts, especially because it's a subscription box, so it's the gift that keeps giving throughout the year. I use Mel Science Kits all the time at home, especially with my kids. So if you want to check them out, you can click the link in my description and use the code JAMES70 for 70% off your first month. Now let's get back to our experiment. Okay, let's try it in just air now. I'm gonna spin it as fast as I can by blowing air on it. It can only go so fast before it flies off by itself, so I'll go right to the point where it starts getting a little wobbly and then measure how long until it stops. Okay, go. Okay, we're a minute into it. It slowed down pretty significantly already. Just past 2 minutes, it's almost stopped. Now it finally stopped at 2 minutes and 18 seconds. Now let's try it in the vacuum chamber. Okay, so in order to do this, I have this tube connected to that piece of wood in there. And on the wood, I have a magnet so I can move it around. And then this tube's connected to the atmosphere and it's pinched at the end. But then I can open it to blow a little bit of air in and start spinning it. Now the chamber volume is huge compared to the volume of air I'm letting in the chamber. And I even measured that letting this little bit of air in doesn't change the pressure in the chamber by any measurable amount. So I'll blow air on it at low vacuum, then close the tube and move it away from the magnet so there's no air motion. Okay, start. Okay, at a minute into it, it looks like it's still slowed down pretty significantly. 2 minutes, we're still chugging along. Okay, I'm gonna say it stops here. So we're at about 2 minutes and 58 seconds. So I was pretty frustrated at first. There's only a tiny increase in spin time, even at 0.1 psi. That's 99% pure vacuum. So why would that be? Well, this is where it got really interesting. If you look at the setup we have of a spinning disc above a magnet and look at the drag effect of air, at any pressure above 100 pascals, there's almost no dependence on pressure. So this regime where there's not pressure dependence is called the continuum flow regime. This means that molecules collide with each other much more often than with the surfaces. So drag depends only on the viscosity of the air, not the pressure. And the viscosity of air is basically constant across a wide range of pressures. But then once you get below about 100 pascals, each molecule hits the surface directly with almost no intermolecular collisions. That's when you actually see reduced drag. In this paper where they did the same experiment as I'm doing here, they found no reduction in spin damping until they reached very low pressures, much lower than what I can reach here. But in their experiment, did it spin forever? Well, still no. At these very low pressures, the drag reached another plateau. And this comes from the fact that the magnets in graphite are not perfectly uniform. There are always slight defects that cause tiny eddy currents, and those eventually slow it down. So even though you can get virtually frictionless rotation at very, very low pressures, it still can't rotate forever. So alas, perpetual motion lies just out of reach, always. And thanks for watching another episode of the Action Lab. If you haven't subscribed to my channel yet, remember to hit that subscribe button, and we'll see you next time.